Welcome back. For the last several episodes, a matrix has been a grid of numbers, something we row reduce, invert, or use to solve a system. Today we change our entire relationship with the matrix. We are going to see it as a function. A linear transformation is a function that takes a vector in and gives a vector out, and it does so while respecting the two operations that define a vector space, addition and scaling. The headline result of this episode is one of the most beautiful facts in all of mathematics. Every linear function from Rn to Rm is multiplication by a single matrix, and you can read the matrix straight off the transformation by watching where it sends the basis arrows. With that in hand, we will build a vocabulary of geometric moves in the plane: rotations, scalings, reflections, projections, and shears. Discover why matrix multiplication is defined the way it is, and meet the kernel and the image. Let's begin. Here is the entire definition, and it is shorter than you might expect. A function t from Rn to Rm is called a linear transformation if it obeys two rules. The first rule is additivity. The image of a sum is the sum of the images. If you add two vectors first and then apply t, you get the same answer as applying t to each and then adding. The second rule is homogeneity. The image of a scaled vector is the scaled image. Scaling before or after t gives the same result. These two rules fuse into a single slogan. A linear transformation preserves linear combinations. Apply t to a combination au plus bv, and you can pull the t inside and get a times t of u plus b times t of v. Two consequences follow immediately. First, the transformation must fix the origin. T of the zero vector is the zero vector because scaling by zero forces it. Second, every line through the origin is sent either to another line through the origin or collapsed onto the origin. Linear maps cannot bend, cannot curve, and cannot shift the origin. That rigidity is exactly what makes them so powerful. Before the big theorem, let's build a feel for what counts as linear and what doesn't, because the boundary is sharper than people expect. On the linear side, a map that sends x, y to 2x and x plus y is linear. Every output component is a sum of constant multiples of the inputs, nothing more. All 5 of our geometric moves are linear, and of course any matrix times a vector is linear by construction. Now the failures. A translation that adds 1 to the x component, sending xy to x plus 1, y, is not linear because it moves the origin, plug in the zero vector, and you don't get the zero vector back. This is the most important non-example, and it has its own name, an affine map. Squaring a component, sending xy to x squared y, fails homogeneity because doubling the input quadruples the output instead of doubling it. And taking an absolute value of a component fails additivity because the absolute value of a sum is not the sum of the absolute values. The classic ways to break linearity are shifting, squaring, and absolute values. If you see any of those, it is not a linear transformation. Now the central theorem, and it is genuinely stunning. Take any linear transformation t from Rn to Rm. I claim it is just multiplication by a matrix, and I can tell you exactly what that matrix is. Here is the argument. Any input vector x can be written as a combination of the standard basis vectors, x1 times e1 plus x2 times e2, and so on. Now apply t and use linearity to pull it across the sum and across each scalar. You get x1 times t of e1 plus x2 times t of e2, and so on. Look at what that is. It is a linear combination of the vectors t of e1 through t of en with the components of x as the weights. But a linear combination of fixed vectors with the components of x as weights is precisely what matrix times vector means, when those fixed vectors are the columns. So the matrix of the transformation has, as its columns, the images of the standard basis vectors. This is the whole game. To capture a transformation completely, you only need to know where it sends the basis arrows. Everything else is forced. Let's put the theorem to work and build some matrices by hand. Start with rotation. We want to rotate the whole plane counterclockwise by an angle theta. By the big theorem, all we need is where the two basis arrows land. The first basis vector, 1, 0, points along the positive x-axis. Rotate it by theta and it lands at cosine theta, sine theta. The second basis vector, 0, 1, points straight up, rotate it by theta, and it lands at negative sine theta, cosine theta. Drop those two image vectors in as the columns of a matrix and you have the rotation matrix, cosine theta, negative sine theta on the top row, sine theta, cosine theta on the bottom. Now scaling. To stretch the x direction by a factor a and the y direction by a factor d, you put a and d on the diagonal and zeros elsewhere. If a and d are equal, the whole plane scales uniformly. Notice the method is always the same. Ask where the basis vectors go and write the answers as columns. The geometry tells you the matrix. 3 more moves round out the vocabulary, and each one is built the same way: reflection. To reflect across the x-axis, leave the first basis vector alone and flip the second one to point downward. That gives a matrix with 1 and -1 on the diagonal. To reflect across the diagonal line y equals x, you swap the two basis vectors, which gives a matrix with ones on the off-diagonal. Projection. To project the plane onto the x-axis, keep the first basis vector but crush the second one all the way down to the 0 vector. Its shadow on the x-axis is nothing. The resulting matrix has a 1 and then a 0 on the diagonal. Projection flattens the whole plane onto a line, so it throws information away and cannot be undone. It is not invertible. Finally, shear. A horizontal shear keeps the first basis vector fixed but slides the tip of the second one sideways by a factor k. Horizontal layers slide past each other like a deck of cards, and vertical lines tilt into slants. 5 moves, 5 matrices, 1 method. Let's watch a transformation act. On the left is the input plane, a clean square grid with the two basis arrows highlighted, the first pointing right along the x-axis, the second pointing straight up. A little unit square sits in the corner. On the right is the same plane after we apply a horizontal shear. Watch what happens. The first basis arrow does not move at all. It still points to 1, 0. But the tip of the second arrow slides sideways, so it now points to 1, 1. The horizontal grid lines stay exactly where they were, while the vertical grid lines all tilt over into parallel diagonals. The little unit square has become a slanted parallelogram. Two things are worth burning in. The origin, marked in red, has not budged in either picture. Linear maps always fix the origin, and the grid lines, though tilted, remain perfectly straight, evenly spaced, and parallel. That is the visual signature of linearity: no bending, no curving, no uneven stretching. Let's put the whole vocabulary on one page. Each panel shows the same reference shape. Think of a capital letter F on a grid before and after one of our transformations, with the original faint in gray and the result bold in navy. First rotation, the F is turned about the origin, rigid, the same size, just pointing a new way. Second, scaling, the F is stretched, wider in one direction and shorter in the other, the grid squares becoming rectangles. Third, reflection, the F is mirrored into a backwards F across an axis. Fourth, projection, the F is flattened entirely onto the x-axis, collapsing into a segment. You can see the information being destroyed, which is why projection cannot be undone. Fifth, shear, the F is slanted, its upright strokes tilting into diagonals while its base stays put. And for contrast, the identity leaves the F untouched. Notice the common thread in every panel: the origin, marked in red, never moves, and straight lines stay straight. That is the signature of linearity, and these 6 little matrices are the alphabet from which planar linear maps are spelled. Here is the payoff that has been waiting since we first defined matrix multiplication. Suppose you apply one transformation S, and then apply a second transformation T to the result. What single matrix does the combined operation? Follow the algebra. The composite applied to X is T of S of X. But S of X is B times X, and then T of that is A times the quantity B times X. And A times B times X, by the way matrix multiplication associates, is the matrix AB times X. So the matrix of the composition is the product AB. This is the real reason matrix multiplication is defined with that row times column rule. It is built precisely so that multiplying matrices matches composing the transformations they represent. Notice you apply the rightmost matrix first because it acts on the vector first. As an example, rotating by 90 degrees and then reflecting across the x-axis multiplies out to a reflection across the anti-diagonal. And because doing S then T is generally not the same as doing T then S, matrix multiplication is not commutative. Order matters in geometry and in algebra alike. Every linear transformation comes with 2 associated subspaces, and they tell you what the map destroys and what it can build. The first is the kernel, also called the null space. It is the set of all input vectors that the transformation sends to 0, everything the map crushes. The kernel always lives in the input space, and it is itself a subspace. There is a clean test hiding here. A transformation is 1-to-1 exactly when its kernel contains nothing but the 0 vector. Because if 2 different inputs gave the same output, their difference would land at 0. The second subspace is the image, also called the range. It is the set of all outputs the transformation can actually reach, and it turns out to be exactly the span of the columns of the matrix. The image lives in the output space. And these 2 subspaces are tied together by the rank nullity theorem from a few episodes ago. The dimension of the kernel plus the dimension of the image equals n, the dimension of the input space. What the map loses to crushing and what it keeps as reach must always add up. Let's turn a rule into a matrix. Suppose a transformation T takes the vector xy to the vector x plus 2y, 3x minus y. To find its matrix, we use the theorem, feed it the basis vectors, and record where they go. Apply T to the first basis vector, 1, 0. Plug in x equals 1 and y equals 0. The first output component is 1 plus 0, which is 1. The second is 3 minus 0, which is 3. So the first basis vector lands at 1, 3. Now the second basis vector, 0, 1. Plug in x equals 0, y equals 1. The first component is 0 plus 2, which is 2. The second is 0 minus 1, which is negative 1. So it lands at 2, negative 1. Drop those two image vectors in as columns, and the matrix is 1, 2 on the top row, 3, negative 1 on the bottom. Let's check on the vector 2, 1. The matrix gives 4, 5, and plugging 2, 1 straight into the rule gives the same 4, 5. The matrix and the rule agree. Let's compose two of our moves and watch order matter. We will rotate by 90 degrees and then project onto the x-axis. The rotation matrix R has 0, negative 1 on top, and 1, 0 on the bottom. The projection matrix P has 1, 0 on top, and 0, 0 on the bottom. We want to rotate first and then project, so the projection acts second, which means we multiply P times R with R on the right since it goes first. Carrying out the multiplication gives a matrix with 0, negative 1 on the top row, and zeros on the bottom. Now let's swap the order and compute R times P instead, projecting first, then rotating. That gives a completely different matrix, with zeros on top and 1, 0 on the bottom. Same two ingredients, opposite order, genuinely different results. Geometrically, this makes sense. Rotating then flattening lands everything on a horizontal line, while flattening then rotating lands everything on a vertical line. The non-commutativity of matrix multiplication is not an algebraic quirk. It is the simple fact that the order of operations changes the outcome. For our last example, let's dissect the projection onto the x-axis, whose matrix has a 1 and then a 0 on the diagonal. We want its kernel and its image. Start with the kernel. Which vectors does this map send to 0? Multiply the matrix by a general vector xy and you get x, 0. For that to be the 0 vector, we need x equals 0, while y is free to be anything. So the kernel is the set of all vectors of the form 0. Y that is the entire y-axis, a one-dimensional subspace. That makes sense. Projecting onto the x-axis crushes the whole vertical direction down to nothing. Now the image, which vectors can the map produce? The image is the span of the columns, which are 1, 0, and 0, 0. That span is all vectors of the form x, 0, the x-axis, also one-dimensional. The map can only ever output points on the x-axis. Finally, the rank nullity check, the kernel has dimension 1 and the image has dimension 1, and 1 plus 1 is 2, which is the dimension of the input plane. Everything balances. A little history, because this viewpoint was hard won. In 1827, August Ferdinand Möbius studied transformations of the plane geometrically, working out how figures move and map onto one another. The decisive step came in 1858, when Arthur Cayley published his memoir on the theory of matrices. Cayley did not define matrix multiplication arbitrarily. He defined it precisely so that multiplying two matrices would correspond to composing the linear substitutions they represent. In other words, the strange row times column rule exists exactly so that matrices model functions. Around the same era, Hermann Grassmann and later Giuseppe Peano developed the abstract idea of a linear map between vector spaces, free of any particular coordinates. And over the 20th century, this became the organizing principle of the entire subject. We no longer think of a matrix as primarily a grid of numbers. We think of it as the coordinate picture of an abstract linear transformation. The function came first. The numbers are just its shadow in a chosen basis. Let's recap. A linear transformation is a function that respects addition and scaling. The image of a sum is the sum of the images, and the image of a scaled vector is the scaled image. As a consequence, it fixes the origin and sends straight grid lines to straight grid lines. The big theorem says every linear map from Rn to Rm is multiplication by a matrix, and the columns of that matrix are the images of the standard basis vectors, so you build the matrix by tracking where the basis arrows go. In the plane, we collected a vocabulary of moves, rotation, scaling, reflection, projection, and shear, each just a small matrix. Composing two transformations corresponds to multiplying their matrices, with the first applied map on the right, and because order matters geometrically, matrix multiplication is not commutative. Finally, the kernel is the set of inputs crushed to 0, trivial exactly when the map is 1-to-1, and the image is the set of reachable outputs equal to the span of the columns. Next episode, we go hunting for the special directions a matrix only stretches and never turns, the eigenvectors, and the numbers that tell us how much it stretches them, the eigenvalues. Today we learned that a matrix is a function. A linear transformation, T takes a vector and returns a vector, and it obeys two rules, T of U plus V equals T of U plus T of V, and T of C times B equals C times T of V. Together these say the transformation respects addition and scaling, which is the same as saying it sends straight grid lines to straight grid lines and keeps the origin nailed in place. The central theorem is that every linear map from Rn to Rm is multiplication by a matrix, and the columns of that matrix are simply the images of the standard basis vectors. So to build the matrix, feed the transformation the basis arrows one at a time and write down where they land. In the plane, this gave us a dictionary of moves: rotation by an angle theta, scaling along the axes, reflection across a line, projection onto a line, and shear. We saw that composing two transformations, doing one and then the other, is exactly multiplying their matrices, which is the real reason matrix multiplication is defined the way it is. Finally, we met the kernel, the set of vectors the map sends to 0, and the image, the set of vectors it can actually reach. Next episode, we look for the special directions a matrix only stretches and never rotates. Those are the eigenvectors, and they unlock the deepest structure a matrix has. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.